In our second approach to this problem, we'll use purely the integration approach. We have two different functional forms for w of x. For x less than L over 2, we said previously that we could write w of x as 2w0 x over L, and for x greater than L over 2, we have w of x equals 2w0 1 minus x over L. We previously found our reactions at A, which we'll represent here. Both of these were positive. FA was equal to 1/2 W0L, and MA was 1/4 W0L squared. We'll break our problems into two intervals. For x less than L over 2, we're beginning from x equals 0, so xp will be 0. Vp will be plus Fa, which will be 1/2 W0L. And then Mp is minus Ma. Again, this difference is because of the difference in sign convention between shear force and bending moment. And this is minus Ma, or minus 1/4 W0L squared. For x greater than L over 2, we'll be integrating our new expression for w of x, and we'll be using our results at the end of the first interval as our reference going forward. So here xp will be equal to L over 2, and because there's no discrete force or couple at L over 2, the values that we get for x less than L over 2 as we approach the interval, as we approach B, will be the same on either side. So Vp will be equal to the value of the shear force for x less than L over 2 as x approaches L over 2 from below, and Mp will be equal to the value of the bending moment from x less than L over 2 as x approaches L over 2 from below. So now we can write our results down directly. For x less than L over 2, our results had given us that V of x was equal to Vp minus the integral from xp to x w of x dx. And that's going to be equal to w0 L over 2 minus the integral from 0 to x 2 w0 x over L dx. The integral just simply integrates to w0 x squared over L. We're evaluating that between 0 and x. There's no contribution from 0 for this simple polynomial, so we simply end up with w0 L over 2 minus w0 x squared over L, and we can pull out a w0L to get 1/2 minus x squared over L squared. So this is precisely the result that we had previously. V of x is equal to w0L times quantity 1/2 minus x squared over L squared for x less than L over 2. For our bending moment, we have this expression. MP is now minus 1/4 W0L squared. We're integrating from 0 to x, v of x, dx. We have 1/2 W0Lx minus 1/3 W0 x cubed over L between these limits. And that will give us a final result. That looks like this for x less than L over 2. If we compare those expressions for what we had with the equilibrium approach, we'll see that they're identical. Now, in order to continue, we have to figure out what v is as we approach L over 2 from below. And if we plug that in, we're going to find once again that we have 1/4 W0L for v, and for m, we have minus 1/24 W0L squared. Okay, those become our values of Vp and Mp for the second part of the problem. So for x greater than L over 2, now we have, again using our expression, we're integrating from L over 2 to x, and in this case the contribution from the lower limit gets rid of the leading term, and we end up with an expression for v of x, which is simply W0L 1 minus x over L quantity squared. For the bending moment, we have this expression, and the lower limit in this case will again contribute a term that cancels out the leading term. And what we're left with is simply a bending moment which is equal to minus 1/3 W0 L squared times the quantity 1 minus x over L cubed. Note that both sets of these expressions are identical to what we obtained with the equilibrium approach. Here we're just integrating from left to right across the beam, being careful to use appropriate values of W of x, xp, vp, and mp as we move from left to right. Finally, let's go back to the figure in example 4 and think about an alternative way to combine these two approaches. The advantage of the two approaches we examined, the equilibrium and the integration approach, is that we add actual functional forms for both v and m over the interval. So it would be easy enough then, having obtained those, to plot those out. But it's also quite a bit of work to derive those functions, and so what if we wanted the shapes of these things without necessarily having to go through all that work? Here we can combine elements of the equilibrium and integration approaches. First, we want to identify key points where we can identify values of v and m. And that's pretty straightforward here. The key points are A and C, where we have the beginning and end of the beam, but also at B, where the nature of the distributed load changes. A is straightforward. We know FA and MA. We know the reactions there, so we know that VA is going to be equal to plus FA, or 1/2 W0L, and we know that the bending moment at A is going to be minus the reaction at A, or minus 1/4 W0L squared. C is also straightforward because it's a free end. There's nothing happening out here, so we know that V at C is 0, and we know that the bending moment at C is 0. We don't have any discrete forces at B, so what we can do is use a single free body diagram, either based on the left or the right-hand side, to figure out what's happening at B, and then we know we're going to get no jumps or discontinuities in V and M. So let's go ahead and choose a free body diagram based on the right-hand side, and we know we're going to have a net force here that is 1/2 the base times the height. The base is L over 2, and the height is W0. So F is 1/4 W0L. And we know that that location is 1/3 of the way from the base, and the base is L over 2. So this distance here is L over 6. And then we have the shear force at B and the bending moment at B. And so our vertical force equilibrium tells us simply that VB minus F is 0, or that the shear force at B is equal to 1/4 W0L. And we can choose to take moments about B, in which case we get minus F times its moment arm, which is L over 6, minus MB is 0, or the bending moment at B is minus 1/24 W0L squared. Here we've plotted the values of V and M at A, B, and C, and we want to again connect the dots between them. So we first use the fact that we know that the slope of V is equal to the distributed load, and we know that the distributed load starts out at 0, so the slope at A is 0, and it's also the case that the slope at C is 0, so we expect our curve to begin and end with a slope of 0. We can also see from W of x that it rises linearly to its peak value at L over 2. That's where its slope is going to be maximum. So we could sketch that in here. And we can also see there's a kind of symmetry to the way this is going to look, because when V starts with its initial value and its slope is 0, it's going to fall until it reaches its maximum slope at L over 2, and then it's essentially going to reverse that process with the slope going from its peak value down to 0. So we're going to end up with then something that looks like this. For m, it starts out at minus w0 L squared over 4 at a, and it has a slope dm dx equal to v, so it's positive. And then that slope is diminishing as we move from a to b to c. So by the time we get to L over 2, that slope is half of what it was at a. And then again, v is 0 at x equals L, so this has to meet L here with a slope of 0. The result of that is a curve that looks something like this. And so we've been able to get a pretty good approximation for what the shapes of those curves look like in this hybrid approach without actually deriving any functional forms. And in fact, if we plotted out the results, we'd end up with the curves that look like this. So in summary, we can use the equilibrium approach, we can use the integration approach, or we can use the hybrid approach. If we actually want functional forms, we pretty much have to use the first two. But if we want the general shapes of the shear force and bending moment diagrams, we can use elements of both to construct these shapes.